the last part of 2.1, which we started last Wednesday. And we just got a little bit to finish up in 2.1. And then we're going to cover most of 2.2 with the remaining part of 2.2 being finished on, actually the remaining part of 2.2, piecewise functions, will be all of Wednesday's class, okay, which you have your handout for. So let's start today with reviewing what we talked about a little bit on Wednesday. We talked about the domain and range for a relation and then a domain and range for a function on Wednesday. However, we have not looked at how do we identify the domain and range from a function if all we can see is its graph. So I've actually taken this from your book. Want to start us off here, Ben? Number 1.
Function y is equal to f(x). So all of the domain of the function is set up all of the range set up all out.
Okay, so if we had this blue function graphed on our paper, wow, excuse me, my earphone fell out. Okay, so if we had this blue function that we're going to call f, and we were trying to talk about what the domain is, we usually describe the domain. There's a couple of ways to recall. We can remember that a domain is a set of numbers. So we could either use set builder notation, we could use inequalities, but with functions, the most efficient way to do that is with interval notation. So we want to try to define the domain and the range using interval notation. So you look at your function, and if it has a beginning point, you find the x value for that beginning point. So in other words, this function starts right here. So you come down to your x-axis, and notice it already has the bracket there, right? Is the bracket. So it says that all of the x values between that point on your x-axis up to whatever this point is right here, we call the domain. So visually, you could imagine having arrows coming down from every point on your function down to the x-axis. Okay, I can't obviously draw an infinite number of these lines, but you could just go down like this. And so every spot that those lines hit on the x-axis is called your domain. Okay, those are all your input values. Okay, what about the range? Well, the range would be the set of all output values. So let's take a look at those. The smallest output value on this function occurs right here. Okay, so if you came over to your y-axis, notice now our bracket is upside down. That would be the beginning. That would be your smallest point of your interval. And then every single value, your output value from here, all the way up to this point right here, which is going to be your maximum value of this function, that goes over, and that's going to be the highest value of your range on your interval. We don't have coordinates for this. We're just looking at the idea. So you can see that every single output value would be defined between this lower output value up to this higher output value, right along there, that green interval. So your domain would be this blue interval along the x-axis. And if we had numbers, we could put them in, right, into interval notation. And your range would be this green interval here. It's all the output values, so domain and range. Now, Ian Winokur actually did a little nice video on Sketchpad. And so here's a function right here. It's defined in 2 pieces. And if this is working correctly, it should be animated. So if I wanted to see what the domain is for this function, and these points right here are actually solid points, even though they have little openings, they're actually solid. It's a nice little animation. So let's see what the domain looks like. Is that cool? I think that's so cool. So if I were describing the domain for this function, could someone tell me what the intervals would be? Notice I used a plural here. What would be the domain for this function? Someone want to give it a shot? What's the smallest value of x that we start with here? Let's see. Here's the first point. We come down. That is 2, right? So the first, your domain is always an interval that goes along your x-axis or your horizontal axis. So we start with 2. And then, Ben, where do we go up to? 6. Then what happens? We take a little rest. This function is not defined from 6 to 7. There's no output values from 6 to 7. So that interval, all the x values on that interval, union with what's set now, what would be the rest of this? How would I describe the next interval? Where do I start? 7. And I go up to 15, right? So that's how I would define the domain. But this visual, I think is really nice. Like seeing this visual happen is like so cool. I've never, I never had anything like that when I was learning. I mean, this animation to see where your domain is. Let's check out the range. So I'm going to hide domain. But look, the interval remains there. Isn't that cool? So you can see it goes from 2 to 6, and we union that 7 to 15. So let's take a look at the range. Okay, now let's hide that, and let's see what intervals we have. So if we were to describe the range, can you try to describe at your seats right now what the range would be? Just give it a shot. See if you can describe what the range is. To yourself. Look. So the range is going to be these intervals along our vertical axis that we typically call our y-axis. What's the smallest number on this y-axis? Excuse me? -2. And my first interval goes from -2 up to a little bit higher than 2, right? Do you see how that line goes a little bit higher? So you're just going to estimate here. What did you call that? 2.2 sound okay? All right. And now we're going to union that with what other interval? We go from 4 to 6. Actually, it looks a little bit higher than 6, actually. So I would have taken 4 to 6, but it looks like 4.6909 or something. Okay? So that's your range. Okay? Now, if we join these two curves, my question is, do we have a function? No, because if I take my vertical line and I move this vertical line, you can see that vertical line hits that function in more than one spot for different values of x. So if x is 10, you see I'm hitting my curve at 2 different spots. So once I join those two pieces, this is no longer a function, it's just a relation. Okay, okay, so that's a really nice, let's give Ian a little hand clap for that nice animation, and I'll have him listen to this part. People that do Geometry Sketchpad, really, I mean, if you really love math and you want to play with something, it's unbelievable the kind of animation you can do with this. Okay, so let's find the domain and range on the function illustrated below. So Adam, you want to read this for us? Okay, so the first thing I notice is I go as far to the left as I possibly can, and I notice that I have this point called -7,6. There's nothing to the left of -7, so the function is not defined to the left of -7, and there's a solid dot at -7,6. So that means my interval will begin at my x value called -7 when I'm listing the domain. So I'm going to start at -7. So if I came down, I could draw a straight line down there, and I could actually use a little bracket like that to indicate that's where I begin. And then I can move along to the right, and for any of these x values that I'm going through, I could go to a point on my red curve as I move along, I move along, I move along. Where do I stop? I never stop, right? Because this curve is never going to stop. It just keeps going. It's a straight line. So what do I put for my end value for my domain? Infinity with a parenthesis, right? Okay, so here's my domain. It's outlined in blue along my x-axis. All right. Now it's time for the range. Home on the range. I can't help it. Every time I do this, I think of that song, Home on the Range. Anyway, should be Home on the Domain, actually, but anyway. They didn't know that, those cowboys, when they made that song. Okay. Who made that? Who actually, does anybody know anything about that song, Home on the Range? Like who wrote it or, yeah, well, not right now, but later. I'd love to know and see if we know anything about them. I don't think they have functions in their background. What you say, Ian? Send me a memo? Okay. It's an Appalachian song? Oh, huh. All right, so how about talking about the range here? Tara, want to read this for us right here? No. Mm-hmm. Okay, so to look for our smallest value, we look below our y, our x-axis is if our function goes below, or we just look for the lowest point. So what's the lowest output value here on our graph? What's the lowest output? Just the output. -2, right? So I come over here and I say, okay, that's where I'm going to begin because that's a solid dot. And then I'm going to go up, 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 up. Do I keep going up forever and ever? Yep, because of this part over here. This continues to go up. So -2 to infinity would be my range. Okay. So I'd like you to do now at your seats is I've given you 3 pictures of 3 different functions. I'd like you to identify the domain and range of each, please. So let's look at this. We have 5 tables and we have 6 spots to fill in. So I'll do the first one, the first domain. The first domain goes from bracket -5, comma 3. Okay, so table 1, what do you have for your range there? You said square bracket 0, 4? Like it's a question mark. How about with a lot of confidence?
4.
There we go. All right, that's absolutely correct. All right, we go, the lowest value here of our output is at 0, and we go up to 4. Okay, table 2, how about the domain? Okay, now why did Mary say a parenthesis at -4? Right, because that point has an open circle. So that means it's not defined, it's not part of the function. Okay, how about the range? Table 3? Right. Similarly, you take the output here with a parenthesis because it's not included in the value as a defined value of the function. Okay, domain, table 4 for the third one. Bracket 4, parenthesis, oh, -4, okay. There we go, that looks good. And the range, table 5, Ian? Yep. Can you tell me about how I represent it with interval notation? I can't just put 0, 0. Okay, so 0 to 0 goes nowhere, right? So it just has one value. So could it be 0? Okay, you want to try it again? Infinity, comma 0. About -infinity, because you have to put your, and then so it has to be parentheses 0. Okay, all right. So domain and range feeling pretty okay so far? Yeah, all right. Let's take a look at this next idea here. So we've got another function defined here. This particular function, if you were to look at this, what would the domain for this function be? From -infinity to +infinity, because this function's going down. You can go out as far as you want in either direction. and it's going to be defined. So the domain here is all real numbers. You could say, you could use interval notation and say negative infinity to positive infinity for the domain. You could go like this, all real numbers. That's another way to say that set, the real number set. You could be really fancy and put an upside down A, which means for all real numbers. That's how we write that mathematically. No, that's just how we write it. Notice the R has a double stem there. That means a set of all real numbers. And what would the range be here? What's the smallest value of your range? Negative infinity. And do we have a highest value here? 3. That's the domain and range. So find f of 0. So f of 0 says what? Find the output value, which we call f of 0, when our input value, in this case our input is defined to be x, when x equals 0. So I go to where x equals 0, and I draw a vertical line right through x equals 0. Let's see if I can get a nice color here. Okay. And now get out of my way so I can draw you. Okay. So I go right through, oops, that's not a very good line. Let me move it over. Go right through x equals 0. And where do I hit my graph? At 3. So the value of my output when x is 0 is the point 3. It's right there, 0, 3. What do we call that point usually? The y-intercept, right? So the y-intercept will always have x be 0, and your output would be f of 0, whatever that happens to be. That's how you can represent the y-intercept for any function. X is always 0, your output will be whatever the function defines at that point called f of 0, that's your output. So instead of writing y here, I write f of 0. That's the notation. Sometimes these notations are new to you, so I'm going to try to use it more often. Now it says for what values of x is f of x equal to 0? So this is a little different question. F of x equals 0 says my output is 0. So now I'm going to be looking for output equal to 0 and looking for the x values where my output from my function is 0. So what x values have my output equal to 0? Negative 3 is one of them. How about another one? Someone else? And 2, right. Okay. So typically in the past, what have we called these particular points? In the past, what have we called those points? Negative 3, 0, and 2, 0. X-intercepts, right? So traditionally, we've called these x-intercepts. Now, you remember when we were doing our graphing calculator to find solutions for equations, one of the methods we used was to find the zeros of a function. And I told you that later on, when we actually define functions, we'd get to why they were called zeros. So when you have functional notation, instead of using the word x-intercept, we say that the points the value negative 3 and 2 are the zeros of this function f. The function's name is f, because these are the x values for which your output, f of x, is 0. The real zeros are what we have called in the past the x-intercepts. So notice I've referred to these as real zeros because your x-axis is the real number line. Okay? It's possible to have zeros that are not real. You use imaginary numbers for that, and that would be if you had a graph like this, for example, and if this function was x squared plus 4, then to find the values of where that is equal to 0 wouldn't be a real number. It would be an imaginary number, a complex number. By the definition of a function, each value of x can have at most one and only one value for y. That's what we've defined as a function. So how many x-intercepts can we have for any particular function? For any function, how many x-intercepts could I have? Infinite number, because For each x value, you're only going to have one y value, which is 0. So you can have an infinite number. Now, what about my y-intercept? So right here, I put my vertical axis, my vertical line straight down through x equals 0, and I touch this graph at one point called 0, 1. How many y-intercepts can I have? At most one, right? Because if I had a graph that looked like this, find to look like that, that would never have any, right? So at most one. Well, are you going to let me get away with that? Is this ever going to hit the y-axis? Yes? I don't know. So how many y-intercepts can we have? We can have one. Question is, can we have none? So that's something I want you to think about. Can you have no y-intercepts? Is it possible to have no y-intercepts? Sure. People say sure, and other people are saying, please don't ask me. I don't know. So think about that, and we'll talk about that on Wednesday. Okay. So increasing, decreasing, and constant functions, the mathematical definition of when a function's increasing, decreasing, or constant looks a little scary. Not too scary. But the idea itself is so intuitive that I want you to just, let's look at the intuitive ideas of increasing, decreasing, and constant functions. Then we'll take a look at the notation, because sometimes the notation, if you go through the notation first, it can get in the way of the meaning of an idea. So every graph tells a story, and we're going to take the story from our book because our author did a really nice job with coming up with a scenario that we can easily, I think, easily understand the idea of increasing, decreasing, and constant. And it's called the time temperature flu scenario. So we're looking at two variables, time and temperature. Time is being measured in the number of hours after 8 a.m. and temperature is in degrees Fahrenheit. Okay? So if you look at our first graph over here, you notice that we have a break in our vertical axis, our temperature axis, because we're not starting at 0, we're scooting right up to 98 degrees Fahrenheit. And we have a couple of points labeled. And so now we just have to interpret each of these points. Notice I've defined this graph to be decreasing, okay? Decreasing. So if I were to ask you, how would this story begin? You close the door on the president. She closed the door on you, Bob. Yeah, we did. Well, we're telling a story about your temperature. How you feeling? Okay, good. So you're not part of this story. Well, this, yeah, someone's temperature is being charted here. I think it's going to be yours in a few minutes. Okay. Maybe. Someone got a temperature of 101 degrees? No. Okay. See ya. Bye. Okay. So if I were to ask you to tell the beginning of this story with time, just what this interval represents right here with time and temperature, what would this be saying? Someone want to tell me what this story would be right here for this first part of our graph? Anybody want to take it on? Okay, so can you tell me any more specifics than that? Yep, degrees Fahrenheit right here, yeah. And when did we start this whole temperature taking business? Right, so when our input value is 0, which means 0 hours after 8 a.m., so that means at 8 a.m., the person's temperature is 101 degrees Fahrenheit. And we notice here, Cameron says that this temperature is going down, 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 down until we come to 3 hours after 8 a.m., which is 11 o'clock, we're at 98.6 degrees. Okay? So when we define the interval that over which a function is increasing or decreasing or constant, It's always going to be an open interval. Okay, so that's a key word here. It's going to be an open interval. So right here, it's going to be an open interval. And your interval is always defined over your input values. Always over your input, never on your output values. Okay, so let's take a look at what open interval is your temperature decreasing on. So if I asked you what open interval would describe where this particular temperature begins and where it's ending right now, where it's decreasing, that interval over which this temperature is falling, what would you tell me the interval would be? From what two values of my time? 0 to 3. And since it's an open interval, it's always going to be parentheses. Okay? It almost looks like a point, so you've always got to know what you're answering. Okay, in this particular case, it's an open interval. That's why we have the parentheses here and here. So the temperature, which we call f of x, is actually falling over all of these time values between 8 o'clock a.m. and 11 o'clock a.m. Okay, so between those two times, your temperature is falling. So that's called a decreasing interval. Okay? Over what open interval is your temperature increasing? Can someone help me with that? Over what open interval would my temperature be increasing? Where my temperature is actually now starting to rise over this particular time interval. Yep, Ben? 3,5. So now you see, and this is really based on the sort of the idiosyncrasies of whatever author of the textbook. Most textbooks will use an open interval, but it's either going to be open or closed, and it just depends on the author. Because you can see here, if you were looking at this middle graph, you would say, what do I do with that 0.3? Do I put a closed bracket on it in one interval and open on the other? So that's why they just say keep the intervals open. And then finally, we have this idea over what open interval is my temperature remaining exactly the same. It's neither rising nor falling. So what would be the open interval where my function is constant? Want to help me with that? 5 to 7, right. So in terms of time, it would be what? 5 hours after 8 o'clock would be 1 p.m. to 3 p.m., right? This person's temperature is remaining constant. So clearly, they probably maybe perhaps took some type of medicine or herbal medicine or drugstore medicine, Western medicine from this time point, and their temperature started to go down. But then maybe they went to school and instead of staying home and resting, and then their temperature started to go back up, and now it's just staying at the same level. So do you agree with me that this idea of increasing, decreasing, and constant is sort of an intuitive sense? Do you feel like you could have answered that? Maybe not the open interval idea, but if you looked at this graph here and I asked you, where is this increasing, decreasing, and remaining the same, do you think you could have answered that? Yes? No? Yeah? Okay. So let's take a look at how we have to do it mathematically, the notation we have to use. So I took this from your book. Well, I actually took it from a place in your book that I should show you now, I guess. This is kind of a cool place to go to in my math lab, and you all have this available. Over on the left-hand side of my math lab, you have something called Multimedia Library. I don't know if you've spent any time in our Multimedia Library, but then when you get your Multimedia Library, you go over here, and there's a window, a drop-down window, or drop-up in this case, and you put in the chapter you're interested in. And then over here, you have every single section in that chapter, including mid-chapter reviews. And then you can say select all, but they have animation, they have interactive figures, they have chapter test prep videos, all kinds of stuff. So notice we're on increasing and decreasing functions. So I'm going to click on that. And this is the function we just looked at. So you can see here there's annotations, and this is what you should see something similar to this on your handout. So notice right now, and we'll highlight the interval. We'll show the function value, the value of the function. If you wanted to know what function was being graphed, there it is. That's a polynomial function because all of your exponents are 0 or bigger. They're all either 0 or positive integers. And if we wanted to, we could see the actual function values along here. Now what's nice is I can use this little slider and move this x value along the way. And I can make my value here larger and smaller. So if we move this back to where we were a minute ago, notice how along your x-axis he now has the parentheses there, your author or the person doing the interactive figure, because it's an open interval. And so what we have to say here is that this interval, x1 being this point called 1.1, the interval from 1.1 to 5.8, whenever 1.1 is less than 5.8, that's this statement down here, as long as x.1 is less than x sub 1 is less than x sub 2, in I stands for interval. Okay, so that I stands for the interval. Then if the function evaluated at x1, if its output value is lower than or smaller than the output value at x2, then we know we're going to be going from a smaller value to a larger value, so we're going to be increasing. So if I move this value of x1 to the right, we still remain an increasing function anywhere along that interval. Okay, that's increasing. Okay. If I wanted to talk about decreasing, then I would move x1 all the way over here, and then I would move x2 so that I was anywhere along this point. Now x1 is still less than x2, but my output function, my output value is greater than my value at f of x sub 2. So it's a little bit, the notation is a little like challenging at first, but if you just look at it, it makes a lot of sense if you're looking at a particular function. I thought I could actually change the function here, but I guess I can't. Okay, so that's the, I'm not going to test you on that notation. I just wanted you to be aware how you would actually read it. So you can see here, you have x1 is less than x2 on the interval I. Remember, I just stands for interval. Just represents some interval. And here's x1 right here. Here's our open interval from x1 to x2. So f of x1 is smaller than f of x2. That's how it tells me my function is decreasing. Because x1 is to the left of x2, but the y value, the output value, is to its right. F of x1, oops, sorry, I put that the wrong way. I wanted to write it as greater than x2. So that's the value, that's how we define mathematically a decreasing function. Okay, so I want you to spend about maybe, whoops, see, I almost did this in my other class too. I skipped this part because I'm used to having separate pages for everything. So let's take a look at this idea. Relative maxima and relative minima. Wow, that's a mouthful. First of all, what does the A on the end of maxima and minima mean? What does the A mean? Does anybody know when you put an A at the end or something? But when I have more than one syllabus and I call it syllabi, what does the I do? Plural. And in this case, the A is plural. Max, I think it is. I could be just making that up, maxima. Notice I'm calling it relative maxima and relative minima. I'm not saying maximum and minimum, which is what because if I said what's the maximum value of something, that there's one and only one value, right? Your maximum, you're the kingpin or the queen pin, right? Minimum means you're the absolute lowest. All right? So this idea of maxima implies is potentially more than one of each of these. What does this word relative mean? It means that within a certain piece of your graph, if you just like cut out a piece of your graph, in that neighborhood, you would be the biggest value if you're a relative maxima. And if you're a relative minima and you cut out just a sliver of this graph, you would be at your lowest point. Okay? I like calling them local. Some books call these local minima and maxima. Some books call them relative. Some books call them both. They use the two terms simultaneously. So let's just describe how a function reaches a relative maxima. So here's the point on my graph. If I asked you for the coordinates of that point right there, what would the coordinates be? How would I define those coordinates? C is my input value, and what's my output value called? F of C. We don't know what it is, but that's how we would write it, C and F of C. So to define a relative maximum, your function has to change from this function as I move along here is increasing, 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 and then I come to this point, and I've sort of reached my high point for the day or the week or the year or life, I don't know, and then I start decreasing, decreasing, decreasing. So notice you have to have something happening on both sides of that point. Okay, so in a relatively short neighborhood, if I blew up my function or I cut out this part of my function and I blew it up, that point would be the biggest as far as I could see. Just like in the old days when people thought the earth was flat, because as far as they could see out to the horizon, it looked flat. So if you're in this neighborhood right there where that green box is, the point C, F of C, appears to be the top of the world. Similarly, if your function is decreasing, decreasing, decreasing to this point called C, F of C, and then you start increasing, if I took out a little piece of that curve right there and I looked from, say, C1 to, say, C2, I looked on that interval, on the interval of C1 to C2, for example, then the point F of C, this value, F of C, would appear to be the lowest. It's the lowest point, the lowest output value on that interval. So we call that the relative minimum, okay, minima, okay? Local, relative, all the same. The point being, it's just within a neighborhood. There's no like one absolute maximum or minimum value. If we have a function where there is an absolute maximum or minimum, we don't even use the word absolute, we just say maximum or minimum value. So I've given you now a little something to hang out with here for a while. Now look at where this curve, let's identify these points here so you're not getting, let's call that point there -5, 0, even though it's not exact. And let's call this point right here, so you all have the same, let's call that -1.10, okay? And let's call this point right here 0, 1, 2, 3, 2.9, just so that we're all using the same values. So I'll take about 15, 20 minutes to work through this at your seats, and when you are all kind of finished and in agreement, put up your flag, or you can just put your flags down now and put it up if you have questions, and I'll come around and help you out. You can compare them with what you have at your seats. Oh, I thought I shut that off. All right, so the domain here is from -7 to infinity. Is that correct? Agreement? Yes. The range is from -2 to infinity. Yes. The zeros of f are -5, -1.1, and 5. That's where the zeros are. You just list them. I didn't ask you for the coordinates of the zeros. Just what are the zeros? The values that make your function 0 are -5, -1.1, and 5. F of 0 is 2.9. Intervals on which f is increasing should be just parentheses, and it says increasing from 5 to infinity, and from -3 to 2. From 5 to infinity. Do people agree with that? 5 to infinity. And then this next one says from -3, which is right here, -3, up to 2. Are we increasing on that interval? Yep. And what did the person forget to put in between these two? Because it was union, right? So when you have more than one interval, you say put them together by union, okay? Intervals on which f is decreasing. -7 to -3 and 2 to 5. 2 to 5. I agree with this one, but not this one. Okay, so why am I disagreeing with this first interval from -7 to -3? Go back to your definition. To be a relative maximum, your function has to change from increasing to decreasing. Is your function changing? Is there anything to the left of -7? No, there's no function there, so you can't change from increasing to decreasing at that point. So this is not a relative maximum. Okay, just the 0.25. That's the only relative maximum, because there's nothing in this neighborhood. There's no neighborhood to the left of this. Oh, sorry. Oh, boo. Okay, erase. Can I do Control Z, Control Z? I'm ahead of myself. Okay, yes, I agree. Do I agree? Is it decreasing? Yes. All right. Values at which x, from which f of x is less than or 0. So what I suggested to someone was for them to take their paper. Let's see if I can do this quickly. Take your paper and just cover up everything. Imagine this is all filled in right here. I think I can even make it filled in if I can remember what I did over here. Let's see. Can I remember what I used to do to fill that in? No. There's something over here that allows me to fill in that. So imagine that this is all filled in. And so the only part of your graph that's below your x-axis starts at -5, goes to -1.1, right? And remember, it was less than or equal to 0, so you have to include 5, x equals 5 as well. And then finally, these are the points I want to make, no pun intended. Aha! Any relative maxima and the numbers at which they occur. The relative maxima on this graph is 5. That is the relative maxima. It's always your output value, 5. It occurs at 2. The relative maxima is 5. It occurs at 2. The relative minima are -2 and 0, and they occur at, it's -2. There's 2 of them, folks. There's -2 in this neighborhood is the relative minima, and 0 in this neighborhood is the relative minima. So there's 2 of them, -2 and 0, and they occur at -3 and 5. So this one should be -2, 0, and they occur at -3 and 5. Okay. All right, so let's move along. That's good. The last thing we have to cover in this section is even and odd functions, and I have a little interactive video from our multimedia library. So let's go to even and odd functions down here. And we should see a picture very similar to what we have. Do you see a picture similar to that on your sheets? Okay, and let's see if I can get them both up at the same time, if it will let me. I don't know if it will. See if we can. Don't think it's going to let me. So what's the first point I have here is 2.5 and -2.5. So let's go over here. Do you see that? Let's take a look at this definition first. It says an even function is symmetric about the y-axis. So what that means is if you took this piece of paper like here and you put a crease right down along the side of the y-axis. Any point to the right of 0, if you go to its opposite on the left of 0, and you folded this across the y-axis, they would be at exactly the same height, the same y value above or below the x-axis. Mathematically, how we write that is if you input x and you input its opposite, their output values are exactly the same. So visually, what does that look like? Here we are at x. X is equal to 2.5. That's my input. My output, f of x, is negative 14.44. If I go to the right to its opposite value, negative 2.5, notice my y value is at exactly the same level, negative 14.44. So let's take a look at what happens, and you can fill in your table as we go along. We'll stop and do some inputs. Okay, so here's this function. This is what we call a polynomial function because here's our equation for it. All of my exponents are whole numbers, and let's show the symmetry in the coordinates as we go along. So my first point that we were at was what? Negative, what was it? 2 point what? 2.5. Oops. Oops. There we go. All right, so notice your table's filled in. 2.5, negative 2.5, negative 14.44. Let's find another input value. So I'm going to take this slider and I'm going to make this large so you can see it. Okay, so let's take this slider and move it. Let's move it this way, up there. So what's my x? What's my input value for x now? What do I put in that table? 3.31. And the opposite of x is, if I don't make this large, it should be negative 3.31. What's my output value for both of them? 19.48. So I'm going to move this along until someone tells me to stop. All right, there we are. What's my input value? Next row of the table. What's my input for x? 0.29. And my output, on the other side, my opposite is negative 0.29. What's my output value for both of them? 8.17. So if I input a number and then I input the opposite, I'm at the same height on either side of the y-axis. Okay, moving this along. Until someone tells me stop. So how many more rows do we have? This will be the last one. So 2.38 is our input. Its opposite is negative 2.38, and our output is defined to be negative 15.56. Do you see that as I move this x value in its corresponding opposite, we will always be at the same output value along our curve? Do you see how that works with this interaction? So mathematically, how we define an even function is right here. If the output of the functions are equal, even if you take the opposite of the input. So if I take a number and I plug it into my function, and then I take a number, its opposite, and I plug it in the function, output values are the same. So you can see here that if I take negative 2.38 and I put it into this function and I raise it to the 4th power, I then square it and multiply it by negative 10, and then I add 9 to it, I would get negative 15.56. If I took its opposite, 2.38, and I put it in here, raise it to the 4th power, square it, multiply it by negative 10, and add 9, I would get exactly the same value. That's the definition of an even function. F of negative x equals f of x. And this is visually what it looks like. As you move along, they're at the same height. Okay, same distance. Notice that how we represent that is, see this red dotted line? The distance from the y-axis to that point, this distance is the same. It's congruent. That's what those two lines mean. Those two line segments from here to the y-axis and the y-axis out to this point are the same distance, same lengths. Okay, so Doesn't matter if I change my function. Let's go down to this function here. Oh, that's not going to be. Let me find another one. Here's an absolute value function. Okay. Notice here I have symmetry about the y-axis, that if I folded this function across that y-axis, whatever points on the right side would have a matching point on the left side. And that's defined this way. So now let's take a look at odd functions. Odd functions, okay? An odd function is symmetric about the origin. So it'd be like taking this picture, flipping it this way, and then flipping it over the y-axis, and then flipping it over the x-axis, or rotating it 180 degrees. Now it has this property. If I put in different values for, I wrote that incorrectly, sorry. It should be this. If I put in opposite values for x, the y values are opposite. So here we go with our input. I put in 1.28, the output is 12.13. If I take its opposite, negative 1.28, it's no longer sitting right beside it across the y-axis. It's down here, negative 12.13. Notice now you're symmetric about this point right here, 0, 0, which tells you the distance from this point to 0 is exactly the same as the distance from this point to 1.2. So the opposite, you have opposite outputs for the opposite inputs. And this is how we write it. F of negative x equals the opposite of f of x. Either one of these is fine, but this is the official. They always start with the opposite. F of negative x equals the opposite of f of x. So if we played around with our little input scene here, oops, it's under Explorer. We go back here and play with this for 1 second. Let's see, let's look at a function. What one did I pick? The sine function here. Now, you don't know sine, but you can still see the symmetry, even if you don't know the sine function. So if I move this value along here, look, you can put in 1.1 for your input. Its opposite is negative 1.1. What about the y values? They are completely opposite. This has symmetry about the origin as I move this. Okay? Just because one person starts to pack up early doesn't mean we all have to. So you can play around with this. I have your exams. I want to just get this started. Hang on.